Large language models are transitioning from passive text generators into active participants in software systems. For years, the interaction was a simple linear path. A user provides a prompt, and the model provides a completion. Even advanced architectures like Retrieval-Augmented Generation, or RAG, remain largely single-shot. A developer engineers a fixed sequence where data is retrieved and then injected into a prompt. The flow of the program is determined entirely by the developer's code before the model is ever called. Agentic AI replaces that linear sequence with a circular cycle. Instead of a one-time execution, the agent perceives its environment, reasons about its next step, acts using a tool, and then observes the result to start the cycle again. This creates an inversion of control. In traditional software, the developer's code calls the model to perform a task. In an agentic system, the model effectively decides which code to run next. It evaluates the current state of the goal and chooses the specific tool or branch of logic required to move forward. Mastering this shift requires a new architectural discipline, starting with the engineering of the atomic loop, standardizing how that loop interacts with external tools, and finally, organizing multiple agents into collaborative networks. By placing the reasoning model at the center of the control flow, we transform it from a chatbot into a central processing unit capable of managing autonomous tasks. The foundational pattern for these systems is REACT, short for reasoning and acting. It provides the structured template that allows a model to combine internal thought processes with external tool use. The REACT loop follows a strict sequence. The agent receives a goal, writes a thought to plan, executes an action via tool, and receives an observation back. At the code level, this isn't magic, it's a stateful while loop. The script calls the model, parses its request for a tool, executes that tool, and appends the result back into the conversation history for the next iteration of the loop. During the act phase, the agent must bridge the gap between text and execution. It produces a structured request, typically in JSON format, that matches a strict schema. This ensures the model provides the exact parameters a database or API expects. Once the tool executes, the result is fed back into the model's context window as an observation. This grounds the model's next reasoning step in real-world data rather than just its internal training. The agent repeats this cycle until it judges that the goal has been achieved, or until it hits a termination condition, like a maximum step limit or a budget threshold. This requirement for structured, machine-readable output is what allows us to integrate probabilistic language models into deterministic software environments. Building a single agent with one or two tools is straightforward, but as agents are tasked with higher-level work, they need to connect to dozens of different enterprise systems simultaneously. This creates an integration bottleneck. Without a standard protocol, every agent framework needs a bespoke integration for every tool. This makes the system fragile and incredibly difficult to update as the underlying APIs or models change. The Model Context Protocol, or MCP, addresses this by acting as a universal central bus. Instead of custom code for every connection, any MCP-compatible agent can communicate with any MCP server, standardizing how tools and data are exposed to the model. The Model Context Protocol defines three core primitives: tools for executing functions, resources for accessing read-only data, and prompts for providing reusable templates. This works alongside the agent-to-agent protocol, which allows agents built on different frameworks to collaborate. While MCP standardizes the connection to tools, A2A standardizes the delegation of tasks between agents. Together, these protocols move agentic systems away from monolithic, hard-coded scripts and toward a more flexible microservice architecture. Even with standardized tools, there is a physical limit to the agentic loop, the context window. Every reasoning step and tool output consumes space, and eventually that space runs out. As the window fills with irrelevant multi-turn history, the model's reasoning degrades, a phenomenon known as context rot. It becomes more likely to hallucinate, ignore instructions, or lose track of the original goal. To prevent this, we use context engineering. This is the practice of curating exactly what the model sees at each step, ensuring its immediate memory is focused only on what is necessary for the current task. Short-term techniques include periodically summarizing past steps to save space, or using structured scratchpads, where the agent can store intermediate notes outside of the primary conversation history. For long-term memory, we use vector databases. The agent stores its past experiences as embeddings and retrieves only the specific memories that are semantically relevant to the current reasoning step. Managing this state is just as important as the reasoning power of the model itself. Without efficient memory management, an agent will eventually collapse under the weight of its own history. As tasks grow in complexity, a single agent loop becomes a liability. Monolithic agents struggle to manage the diverse contexts required for large-scale enterprise workflows. This is why we use orchestration patterns, different structural layouts for routing control between specialized agents. The three most common are the state-machine graph, the hub-and-spoke crew, and the hierarchical tree. Graph-based orchestration, used in frameworks like LangGraph, models steps as nodes in a flow. It is built for durability, allowing for explicit state checkpointing and human-in-the-loop approvals in long-running critical processes. Role-based orchestration, like CrewAI, assigns agents to specialized roles with specific backstories and goals. A manager agent coordinates the handoffs, which is effective for replicating business processes like market research or content creation. Hierarchical orchestration uses a lead agent to decompose a goal into subtasks, which are delegated to specialized subagents. This tree structure keeps the context for each subagent small and focused. Because each subagent only receives the data relevant to its specific slice of the problem, this pattern is highly efficient at managing the overall context budget. Selecting the right topology is a foundational design choice. Aligning the system's architecture with the actual structure of the workflow is what separates a fragile prototype from a reliable production deployment. Unleashing autonomous loops with access to external systems requires a rigorous approach to safety and governance. The primary risks are compounding errors and unintended side effects. If an agent misinterprets a tool's output, that error can cascade through every subsequent step in the loop, leading the system far away from its intended goal. Mitigating these risks requires strict architectural guardrails. We apply the principle of least privilege, giving agents only the specific tools they need, and run all code execution in isolated, sandboxed environments. For any irreversible action, the system must be halted by a human-in-the-loop checkpoint. The agent's state is persisted while it waits for a person to verify and approve the tool call before it can proceed. We also set hard limits on step counts and token budgets. This ensures that even if an agent enters an unproductive loop, it will terminate automatically rather than consuming infinite resources. Because behavior here is emergent, they aren't evaluated like simple chatbots. Testing requires task completion benchmarks like SWE bench, measuring if the agent actually resolved a problem across multiple steps. Ultimately, building Agentic AI is an exercise in rigorous systems engineering. Real autonomy isn't just the model's intelligence, it is a product of the scaffolding we build to control, ground, and govern that intelligence.